Okay, here I wanted to go over a couple application examples just so that you would have some help with some of these application problems. What you'll notice about exponential and logarithmic problems is that these applications tend to be a little bit longer, a little bit bigger. So as you can see here, this is like a whole big huge paragraph. But essentially it's filled with a lot of information that is unnecessary. So if we were to read it, you can see what is going to be necessary or needed information and what is just extra stuff added in. So here it says the past research tells us that our bodies grow at a given rate based on our DNA and environmental factors in which we grow up. Assuming that a baby girl is born and is 22 inches long, if we consider that the baby will grow at a rate proportional to her body size until adulthood, then the percentage of her adult height attained can be modeled by the following function. So here we are given the function that we need to use. So we're given this function here. And it says where x represents her age in years between 0 and 25. And then f of x represents the percentage of her adult height reached at age x. Okay. So here it says what percentage of the girl's height is attained by age 12. So since the problem told us that x equals age, and we're telling you that we want to know what happens at age 12, all we really have to do is plug it in. So we are going to look at f of 12, and anywhere you have an x you have to plug it in. So this becomes 22 plus 55 log of 12 plus 1. So when we do that, we're going to work this kind of the same similar way that we were working our exponents. Okay, so over here we have our calculator, and notice on my calculator my log and natural log are on the same button. So here when I do this, I'm going to have to hit the button twice, because if I hit it the first time, notice it says natural log. Hitting it again changes that over to the log function. So depending on your calculator, you may have to hit it once or you may have to hit it more than once. So I would start with this log first, and I would do the log of 12 plus 1. Well, we know that's 13. Close your parenthesis and hit enter. Then once you've done that, we now need to multiply that number, so times by 55. And then we have to add 22. So we get 83.266%. We will round that up. Since it doesn't tell you how to round in the problem, you could be safe to round to the hundredths. So this is going to be 83.27%. Okay? And so that's what we needed. So if you notice, we had lots of writing, didn't need nearly any of it at all. Okay, so be very careful when you're reading these that you pick out only what is necessary for you. Alright, let's look at a different one. Here it says the pH of a solution is defined to be the negative log of the concentration, where H3O plus is the concentration of hydronium ions in moles per liter. Solutions with a pH less than 7 are said to be acidic, whereas those with a pH greater than 7 are basic. If the sample of orange juice is determined to have a concentration of 1.58 times 10 to the negative 4 moles per liter, what is the pH? And then the secondary question is the juice considered to be acidic or basic? So we know to find your pH says we have to do negative log of my concentration, H3O+. Well, in our problem, we told you that H3O+ is represented by 1.58 times 10 to the negative 4. So this is going to be the negative log of 1.58 times 10 to the negative 4. So again, you're going to use your calculator. And so here, notice next to my E button is this 10 to the button. So that is what we're going to need. So we are doing the negative and then log of 1.58. I got to hit that button twice to the negative 4. So notice I have this little 10 here. That's your scientific notation. And then you're going to hit enter. And here we get 3.801. So we have a pH of 3.801. And so that's the first part. Now the second part wants to know if it's acidic or basic. And so here, since the pH is 3.801, which is less than 7, the juice is considered acidic. Okay. Now the last problem we have is this one here. It says earthquake intensity is measured on the Richter scale in the formula below, where I naught is the intensity of a just discernible earthquake, and I is the intensity of an earthquake being analyzed. So just discernible earthquake essentially means an earthquake at 0. I mean, you can't feel it. We have to call it just discernible because if you think about it, the tectonic plates are constantly moving. They're never really stopping. Therefore, you always have earthquakes underneath you as the land moves over the lava field it sits on, or the magma that it sits on. However, most of the time when you're, say, sitting in your house, you don't feel anything. So the Richter scale might be somewhat picking up a 0, but we don't feel it. The intensity being analyzed is when you are actually feeling the earth shake beneath you. And so we're going to use this formula here, which is the same formula that is used in the actual science field. And this is somewhat of what they do in order to calculate the intensities of these earthquakes. So the problem says the January 2001 earthquake in India was 80 million times as intense as a 0-level earthquake. It says, what was the Richter scale ranking of the devastating earthquake? So my intensity, the I, is 80 million. Whereas a 0-level earthquake would be like a 1. So here, my Richter scale is going to be the log of 80 million to 1. Okay. So here again, you're going to put that in your calculator. So you're going to hit the log button and you're going to put in 80 million. And when you hit enter, it comes out as 7.9. So we would say that the devastating earthquake was a 7.9 earthquake. Okay. So those are three different types of examples that you may face when dealing with exponential and logarithmic problems. As always, if you have any questions, please let me know in the discussion board or in the comments below, and if not, then see you next time.